السلام عليكم.
السلام.
بالنسبة لتسليم ريبورت بتاعت المعمل، في لسه ناس ما سلمتش التقارير. يعني عدد الناس المكتوبين على التقارير اللي جات لي أقل من عدد الطلاب اللي في المادة. فهل في لسه حد ما سلمش؟ تقارير اللي هي السابقة من 1 ل5. طيب يعني in any case, just in case you haven't submitted your lab reports, please do that as soon as possible because I want to give the lab engineers that enough time to grade them again. Okay, I want you to have the grades as soon as possible. Basically, today we're going to talk about the last topic of this course, which is going to be the sensors. My expectations is basically I should be able to finish that topic within this week. So basically, after that, we're not going to get any new material. We're not going to be adding any new material. I was planning to add a few other topics, but actually I cannot include them in the exam because it doesn't make sense to give you a new topic in 1 week and the next week I examine you the final exam including that topic. So basically, whatever we have in this topic, in this current topic, will be the last to be included in the final exam. Okay, so hopefully after this week, you're going to be focusing on reviewing the material of the course, finishing your assignments, submitting your reports, things of that sort. Okay, so that you have enough time. I know that you have multiple courses and you probably have other assignments, you have other exams and things of that sort, in other courses. So basically, I want to give you the chance to finish everything without being rushed, on all courses at the same time, okay? So basically, after this week, I'm going to be available only for questions. I'm not going to be adding any new material or any new topics to this course. Okay, do you have any questions about that?
Doctor?
Yes.
I have a question about the lab part.
Yes.
Is that we should simulate the labs, but
yes.
Like, is there any recommended simulation program or just?
I think you should ask lab engineer. Do you have his contact?
Yes.
Okay, you can just ask him. I thought what he told me actually was that you already did that in the other experiments.
Simulation?
Did you do any other simulations before? You haven't done any simulations before in the other experiments?
Maybe not simulations, but we just draw the circuits in like programs.
Okay.
Like piecewise.
I tell you what, please ask the lab engineer and see what he tells you. If you feel that what he asks you to do is beyond what's left in the what the time left in this term, please let me know and we will work out something instead of that simulation part. Okay, just ask the lab engineer what he needs or what he recommends for this simulation, and if it's too much, let me know. Okay.
Okay.
Any other questions regarding the assignments? So basically, I just want to emphasize again that you should submit your lab reports as soon as possible because we don't have much time. And basically, you will need to have your grades ready well before the final, okay? One very important thing is that what the faculty recommended is that we will have an assessment. Basically, it's not going to be like, basically it's going to be the final exam, but we will agree together on how to do it and when to do it, okay? And basically it's going to be based on Blackboard, like the midterm. And basically, as I was telling you, this topic is the last topic in this course. And basically, after this week, you have plenty of time to review the material, or basically, if you want me to revise any parts or basically review any parts for you or answer any questions, I'll be ready to do that. but I mean, you can determine the time of the final exam together anytime from start of next week till basically till the end of Shaban, probably. Okay. So basically, let me know based on your other courses, because I know that you have, first of all, you have 33 students, and each of you is taking probably different courses. So it's very difficult for me to set a date, not knowing what the other courses are demanding from me. So please try to come together and basically agree on a date for the final exam and let me know of it. But basically, the last topic that will be included in the exam will be the topic that we're going to start today. Okay?
Okay.
Okay, so basically, hopefully by next Tuesday, I would like you to answer me on basically the lab, the simulations in the lab, whether they are would be feasible for you or not. And also, if you agreed on a date for the final, please let me know of it, okay? I'm fine with any time and any date. Whatever you agree together, I'm fine with it. I'll basically arrange for whatever you agreed upon to be the case for the final exam, okay? Okay, so the final topic actually is one of the most interesting in this course. Basically, if you ask me about the interesting parts in this course that will be very useful for you later on, the first chapter is very important regarding the units. The part about the error analysis is really important because you probably run into it in one way or another, in basically in your project, in working after you graduate. It's very important. And basically, the several measurement instruments that we talked about, the ideas of how they work and their loading error and the measurement theory in general is very interesting. And then this part about the sensors is interesting also because eventually you're not going to be measuring only electrical quantities. You're going to be measuring physical quantities. You're going to be measuring chemical quantities. You're going to be measuring speed or flow or something like that. So basically, what you need to have is a device that would convert the quantity that you want to measure into an electrical quantity so that you can basically use the basic method that you studied for measuring electrical quantities to allow you to measure it. Okay? So basically, let's get into the parts. We will talk about this. So the sensor, by definition, is a probe to register measured events. Okay? So basically, it's just you have events, and these events may not be electrical. They can be anything, basically. It can be mechanical, it can be chemical, it can be anything. It can be electrical, but it might not be electrical. And basically, there is a difference between a sensor and a transducer, okay? The transducer, basically, it transduces the primary measurement signal into a secondary signal by itself. So basically, the secondary signal is usually an electrical signal, basically. Sometimes you need to convert the physical quantity that you're trying to measure into a primary measurement signal. For example, in some cases for biomedical sensors, for example, you want to measure the concentration of a particular substance in the blood, for example, okay? So basically you have a particular sensor that would convert the concentration into basically light, for example, okay, intensity of light. And then you measure that intensity of light using a transducer to convert it into electrical quantity and measure it as voltage or current or whatever. So basically you have concentration, which is a chemical quantity. You converted that to light. This is a primary measurement signal. And basically you use another transducer to basically transduce it from light into electrical signal. So usually transducer is meant for a sensor that would convert a physical quantity into an electrical signal. A sensor might not actually do that. So basically the sensor itself might have might convert another one way or one physical quantity to another. For example, concentration into light, or concentration into, for example, impedance, okay, something like that. then you need to measure that particular change, that first primary signal or primary measurement signal, you need to measure it into an electrical quantity like voltage or current eventually. Okay?
Doctor,
Yes.
can we say an example is, for example, the LDR? So the LDR will be the sensor part, but then it's converting light into resistance. So we need another transducer to convert resistance to voltage.
Yes, basically you will need to do that. But actually sometimes when you have resistance, it can actually be converted very, very simply into, yes, you can probably consider the resistance itself as an electrical quantity, but sometimes people restrict the electrical quantities into voltage, either voltage or current. So if you consider the resistance as an electrical quantity, then the LDR is just a transducer. Basically, it converts light into electrical quantity, which is a resistance. If you consider the resistance as something prior to voltage or current, then you will have to convert it into voltage or current using a very simple op-amp circuit, for example. Okay, so basically it depends on what you think. What people usually do is consider basically, if you have a resistance, this is an electrical quantity, and it's very simple to measure a resistance using whatever things that we did before. So basically consider the electrical quantities as the things that we try to measure in the analog DC circuits or the analog AC measurement systems, okay? So we measured voltage, current, resistance. So if you can convert any physical quantity to any one of these, then you already converted that physical quantity into an electrical quantity, okay? So the LDR in this case would be basically a transducer. It takes a light signal and converts it into basically a resistance which can be measured using the techniques that we used before. Is that clear?
Yes.
Okay. So basically, let's think about the ideal sensor requirements, or basically, what if I wanted to specify the ideal characteristics that I would like to have in any sensor, okay? First of all, you'd like to have what's called feedback-free registration of the signals, meaning that you don't have to get feedback from somewhere in order for you to measure that signal. So for the example of the LDR, for example, you don't need any feedback from the user in order for you to be able to measure the signal, for example, okay? If you're trying to measure temperature, for example, if you use one of the temperature sensors, you don't really have or need a feedback from a user or something like that in order for you to measure the signal. So basically, feedback-free, meaning that when you measure the signal, you don't need feedback from the user to be able to measure the signal. Basically, we're going to go over these. These are actually like ideal characteristics that we're going to talk about in a quantitative manner using sensor characteristics in just 5 minutes. Okay. The second item here is provide reproducible measurement results. What's the meaning of reproducible? What's the meaning of this?
Meaning you get the same results.
Right. So basically, when you repeat the measurement, you get exactly the same results. At least you don't get far from the major or the main result that you got before. Okay. So for example, if I measure temperature, the human temperature, and basically using a particular device, and I get measurements like 37, 38, 39, 35, would that be considered reproducible? If I measure temperature, the human temperature, okay, and the results were like included values like 35, 37, 39, 40, 31, no. Would that be considered reproducible measurement?
No.
Of course not, yes. Okay. So basically you need to have it like 37, 37.1, 39, 36.9, things of that sort in order for you to consider it as reproducible. We're going to see a particular quantitative measure that actually looks at this particular part. Transmission behavior has to remain constant for a long time. What's the meaning of transmission behavior? Transmission behavior meaning that if I convert a particular physical quantity into an electrical quantity, the relationship between the physical and electrical quantities should basically remain the same for a long time. It doesn't deteriorate with time. Okay, for example, if I have a particular intensity of light produce a certain change of resistance, okay, this relationship has to remain constant for a long time. If it changes much a long time, you know, when time passes, then it will not be very useful then, okay? In order for you to have a useful transducer, it should actually measure the same quantity, basically the same way over a long period of time. For the production, basically you can actually produce very accurate sensors in the lab. You can tweak things, and you can, for example, if you consider the example of resistors. You have resistors with tolerance of 10%, okay? If I want to have, for example, if you have 1K resistors with 10% tolerance, if I wanted to do a very accurate experiment that requires exactly 1K, what should I do? I can basically go to the lab and basically look at the drawer where the 1K resistors are placed. Basically just open where, you know, المكان اللي فيه ال 1K resistors الموجود في المعمل. Just open it and basically get like 100 resistors and measure each one of them. Would you able to find one that is exactly 1K? Very much it's very likely that you can do that, because basically you have tolerance 10% doesn't mean that you're always 900 ohms or 1.1K. You can have, sometimes you have resistors spanning the range from 900 ohms to 1100 ohms. So basically, if you look at enough resistors, you will be able to find one that is close enough to exactly 1000 ohms. So basically, doing an experiment in the lab, that basically you can have tolerance in the production, like the resistance, for example, you have 10% tolerance. And basically in the lab, you can select the one that exactly matches what you need. For basically, if you want to have a sensor that will be basically used in a consumer electronic device, okay, example, like if you imagine that you have a device that measures, for example, temperature, okay? If I want to produce a temperature sensor that can be used, you know, in devices that are produced by the millions, then I have to have narrow production tolerances, meaning that if I produce this particular sensor and basically say that this sensor will have an error or a tolerance of 10% or 1% even, okay, if I produce it 100 times, I can actually still get that tolerance for all of them, okay? Production processes actually are very complicated, okay? Imagine that the people who produce biscuits, for example, or chocolate, okay? Do you imagine buying a chocolate of a particular type today and another one tomorrow and feeling the difference in taste between the two? It's probably unlikely that you will feel that. This means that the producers of chocolate or producers of biscuits basically use very accurate measurements for the components or ingredients of this particular product, so that when they produce it today or tomorrow, the outcome will be exactly the same, okay? So basically this is related to the manufacturing processes, and this is very important, okay? Otherwise, you might have a sensor that works really well with you, and sometimes if you wanna basically repeat that, basically use that sensor in other applications, whenever you buy a new sensor, it's gonna come in a different tolerance, which is not acceptable actually for basically commercial electronics. Ideally, it should have a small mass and a small volume, okay? It doesn't make sense if you have, for example, in your mobile phone, you have a sensor that senses GPS, basically. GPS actually, it has a sensor inside that actually can detect the signals from the GPS and basically can compute the location, okay? What if this GPS sensor is like 10 centimeters by 10 centimeters, Okay, would that be acceptable? Of course, it's not going to be acceptable because basically you need to use it in particular products, and usually the smaller the mass and the volume, the more likely the product will be more successful. So basically, the smaller the sensor and the smaller its volume, that would be actually a better thing for a sensor. The application should be simple and manageable. Application meaning that if you want to get a sensor, you don't really want to have a complicated circuit in order for you to be able to use it, okay? If you have a sensor, for example, temperature sensor, as we will see at the end of the lecture, there are temperature sensors that basically you don't have to have analog electronics with it. So basically it communicates with you directly the digital temperature, okay? So basically it would be very easy. You can just place it next to the microcontroller that you have and basically have it communicate with the microcontroller the value of the temperature without having to have a complicated electronic circuit to interface it to a digital side. For the biomedical engineering sensors, which is basically biomedical engineering sensors are probably the most important among all sensors because actually they deal with the human beings. You need to have something called high biocompatibility. Biocompatibility meaning that if you use this sensor on a human being, you're not going to cause any allergic reaction, you're not going to cause any toxic reaction, you're not going to cause any harm to the human being that you're going to use the sensor on, okay? So it doesn't make sense, for example, to have a sensor that radiates, for example, radioactive activity or something like that. And basically, if you use it on a human being, after a while, this human being would be severely harmed because of that radioactivity. If you have a sensor that, for example, that is made of material that is basically toxic to the human being, after a while, it's going to be a problem. So basically, biocompatibility is very important. This is actually very unique to biomedical application. Low stress to patients, okay? Low stress to patient meaning that if you use it on a subject, it's not gonna basically cause the patient to be stressed, meaning that if you use it for a while, the patient will still be okay with it. He's not gonna suffer any problems or anything like that. Imagine that for some patients, they have to have an ECG sensor attached or glued to their chest for a long time. After a while, in this particular location, you're probably going to have a problem because of the adhesive that is used. Okay, so basically, this can be stressful if you use it for a long time. So basically, this might not be a good sensor to use for a long-term application. Okay, some things like some sensors, basically like the blood pressure cuff. The blood pressure measurement device. It has to inflate a cuff, and basically this inflation causes a patient sometimes to feel that he's not feeling his lower part of his limb, something like that. So basically, if you use it for a long time, this can be actually stressful. If you use it once, it's fine, but if you use it for a long time, it might not be as nice, or it might be stressful to the patient. Another very important characteristic is that the sensor should allow cleaning, disinfection, and possibly sterilization. If you imagine that you have a medical device that uses a particular sensor, and this particular sensor is used on a patient that has an infectious disease, okay? How about if you want to use it on another patient? You cannot use it basically direct from one patient to another. You have to actually be able to clean it. If something spills on it or something like that, you have to be able to disinfect it, and ideally you should be able to sterilize it. Disinfection is usually done by means that are like you use alcohol or something like that to basically rub the part that might be infected, and that's it. So basically it's like the disinfectants that we use basically, like Dettol or things of that sort. Sterilization actually is much more complicated process, and it ensures 100% killing of all types of microbes, but it requires basically usually it has steam, very what you call overheated steam, and combined with high pressure, and it has a particular cycle where it actually does that several times. And basically, this ensures a complete sterilization of whatever device that we use. Usually for electronic devices, sometimes it's really difficult to do sterilization, but at least you should be able to do disinfection, okay? So this is one of the very important things. So basically, all these are like ideal requirements for a sensor, but we don't have to meet all of them, okay? At least for a particular application, we have to think about, or at least we have to compare the options that we have in terms of these ideal requirements. Let's now get into how to classify sensors. First of all, we classify them as either active or passive. Passive sensor does not need any additional energy source, meaning that it directly generates electric signal in response to an external stimulus. Okay, meaning that electrical signal, meaning that it's voltage or current. Okay, for example, we're going to see something called thermocouple. We're going to see something called photodiode, something called piezoelectric transducer. For thermocouple and piezoelectric transducer, they actually produce voltage. Okay, the thermocouple changes or converts temperature into voltage. The piezoelectric transducer converts pressure into voltage. The photodiode converts light into current. Okay, so basically they don't require any external circuit at all. They produce voltage or current directly from the sensor itself without having any power source. So that's why they call it passive. Passive because they do not require any external energy source to operate. Active sensors, on the other hand, require external power for their operation. Okay, the external power is usually called excitation signal. Don't worry about it, just consider that require external power. Okay, the excitation signal is modified by the sensor to produce the output signal, or the external power is modified by the sensor to produce the output signal, which can be voltage or current. An example of these is like thermistors. Thermistors are like the type of resistor, nonlinear resistors that we talked about maybe last week or something like that. Thermistors basically convert temperature into resistance. And basically, when you have a resistance, you cannot measure it directly. You have to actually convert it to voltage or current. So you basically, when you do that, you have to insert the thermistor into an op-amp circuit. And basically, this op-amp circuit will not work if you don't have an external power. Okay? So basically, you have to do that. You have to convert the resistance into voltage or into current using an external circuit that requires a power supply. So basically, this converts temperature into resistance. There is also another type of resistive strain gauge. This actually converts strain which is basically the increase in the length of a certain material with stress. So basically, resistive strain gauges also convert strain into resistance. They cannot work by themselves. If you put them and try to measure voltage or current, you're not going to get anything without having a power supply. You have to connect it to a power supply in order for you to get a voltage or a current that depends on the change in the resistance in each one of these sensors. So basically, whenever you have a sensor that requires power supply, that requires any type of external power to operate, then basically we call it active sensor. If it doesn't need that, if it produces directly a voltage or a current, then it's a passive sensor. We can also classify sensors into absolute or relative. Absolute sensor detect a stimulus in reference to an absolute physical scale that is independent of the measurement conditions, meaning that there is a difference between measuring the temperature as 30 degrees and measuring the temperature as 10 degrees above this particular reference. Okay, so basically absolute gives you exactly the quantity as it is. If you're measuring, for example, light intensity, it just gives you the quantity of light, okay? If you're measuring a pressure, it gives you exactly the pressure right away, the quantity that you're trying to measure. The quantity try to measure, if I talk about absolute quantity, I mean that it's relative to the unit of measurement. It's not relative to another reference or something like that, okay? So basically, an example of that is a thermistor. Thermistor, basically, it measures temperature, but actually it measures temperature as absolute temperature, meaning that you can actually relate the electrical resistance directly to the absolute temperature scale of Kelvin, okay? There's a difference between this sensor and the relative sensor of temperature that is called thermocouple. Thermocouple is actually produces an electric voltage that is a function of the temperature gradient across the thermocouple wires. So basically, you have two ends for the thermocouple, okay? And basically, the thermocouple will produce a voltage that is related to the difference in temperature between its two ends, okay? It's not absolute. It's basically relative because it relates the temperature in the area that you want to measure to another reference that you selected, okay? So basically, you're not going to get here the temperature in kelvins. You got the delta temperature. So you have to know the temperature of a reference in order for you to get the absolute value of the temperature in the relative sensors, okay? So basically, for relative sensors, you have a signal that relates to some special case. So basically, you're going to get a delta here. You're going to get an absolute value here. Delta meaning that what you're trying to measure relative to another condition or another situation, okay? Like a particular reference that you select. Here, you get it directly right away. You get the temperature right away without having a reference. It's reference to the temperature scale. That's it, okay? There are many sensor specifications that basically change between different types of sensors. Basically, there is a long list of specifications. We're going to go over the most important of these one by one. So we start with sensor sensitivity, okay? Sensitivity is typically defined as the ratio of output change for a given change in the input. So for example, if you have a sensor that has a characteristic like this, you have two sensors. One of them was like this, okay? Sensor A, whenever you have a change of 1 millimeter, you get an output of 100%. Another sensor B, basically the curve for the sensor B is like this. Whenever you have 1 millimeter, basically you give an output of 50%. Whenever you have 2 millimeters, you get an output of 100%. The sensitivity for A is higher than the sensitivity for B, because for the same exact change here, you got a higher response from sensor A than sensor B. Is that clear?
Doctor, can you repeat it again?
Okay. Basically, the sensor is the ratio of output change for a given change in the input. Consider these two sensors. You have this particular change in the input. This is the displacement. It takes displacement and gives you, for example, voltage, okay? And this voltage is like from 0 to 100%, okay? If you have 1 millimeter change here, for sensor A, you're gonna get 100%. For sensor B, you're gonna get 50%. Then A has a higher sensitivity over sensor B. Okay, so basically it can be defined as the slope of the calibration line. Basically, if you have a line like this, if you have a characteristic between the output and the input for the sensor, it's basically the slope of this curve, basically. Okay, so the slope here, you have a higher slope here than here, then this means that the sensitivity here is higher than here. Okay, the slope by definition is the delta output over delta input, delta Y over delta X. Okay.
Okay.
Is that clear now?
Yes.
Okay. So here for this particular example, you have a higher sensitivity for A than B. A practical example, if you have a temperature sensor, we have 4 types of temperature sensors here. One of them has a sensitivity of 2 millivolts per degree centigrade. This is 40 millivolts per degree centigrade. This is 0.05 millivolts per degree centigrade. This is 1 microampere or 1 millivolt per degree centigrade. Which one of these is the highest or is the most sensitive? Which one of these is the most sensitive? Basically, per degree centigrade is basically, this is a change in the input. Whenever you have a change of degree centigrade, 1 degree centigrade, you're going to get a change of the output here of 2 millivolts. For a thermistor, you're going to get a change of 40 millivolts. Here, you're going to get a change of 0.05 millivolts. Here, you're going to get 1 millivolt. Which one of these is higher?
The thermistor.
The thermistor. So the thermistor will be basically the most sensitive here. Okay? So basically, whenever you have a higher sensitivity, this means that a very small change in the input will produce a large output, a large change in output. Okay, so basically, whenever you have a sensitive sensor, it allows you to measure very small variations in your input. One very important issue also is the sensor dynamic range. The dynamic range of a sensor corresponds to the minimum and maximum operating limits that the sensor is expected to measure accurately. Okay. Sometimes they call it the stimulus range or span. Sometimes they use a different term for them. Okay. So basically, for example, when I tell you that you have a temperature sensor that can measure from, for example, 0 degrees centigrade into 50 degrees centigrade. Okay. This doesn't mean that its output doesn't change after that or below that. Okay, if you have 60 degrees, it's going to have an output, but actually it's not going to be accurate. You're not going to be able to use it to produce accurate results. So basically, the dynamic range is the range in which the sensor would work basically as designed for. Okay, so if you go beyond the sensor range, you're either going to destroy your sensor or you're going to get inaccurate results. There are really very wide variations for such dynamic ranges. For example, I'm actually taking the example of temperature sensors because actually they have wide variety other than other sensors. Basically, temperature in particular is widely used. So basically, there are very different types of temperature sensors that are produced, for different applications. For example, if you have platinum RTD, the dynamic range is from minus 200 degrees to 500 degrees centigrade. Thermistor is minus 40 to 260. Thermocouple is from minus 270 to 1750. Okay, at least this is one type of thermocouples that does that. Temperature IC, temperature integrated circuit, basically is from minus 55 to 150. Okay, let me ask you the question. Okay, basically the selection of the dynamic range is basically based on the application that you're going to use the sensor for. Okay, so for example, if I wanted to measure the temperature of a human being, okay, I need to select a sensor that has the temperature, the expected temperature, or the range of temperatures expected from a human being within the dynamic range of the sensor. Which one of these sensors would be suitable for measuring temperature from a human being?
IC.
The IC. Okay. Any other different solutions?
Thermistor.
Actually, all of them. 37 degrees centigrade is exactly in the middle of each one of them. Do you see one of them that doesn't allow 37 degrees centigrade to be included in its dynamic range? It's present in all of them. So basically, they all can be used as temperature sensors for human beings. Which one is used is different, okay? I'm probably going to reject some of them because actually they are not going to be suitable because of they are relative, for example, but actually, from the point of view of dynamic range, they can all be suitable, okay? Because basically here, first one, minus 200 to 500, you have 37 in the middle. Minus 40 to 260, 37 is there. Thermocouple minus 270 to 1750, also 37 is included. Minus 55 to 150, it's still included there. So basically, you don't have any, from the point of view of dynamic range at least, there is no objection to use any of these sensors to measure the temperature from a human being. The problem comes when you're trying to measure, for example, the temperature in a steam sterilizer. Steam sterilizer, you might have temperatures really high, okay, that are really high. So basically, you might need in a temperature, in a steam sterilizer, as I was telling you, you actually have to have really very high temperature for the to be able to measure the steam temperature, and these can be basically in the hundreds of degrees centigrade. Basically, in this case, probably RTD would be very suitable, thermocouple would be suitable, thermistors and temperature ICs are not, because they are not really basically, they do not basically cannot withstand 400 degrees, for example, or whatever, in both cases. If you're trying to measure the temperature in, if you're trying to melt iron, for example, if you basically use really high temperature furnaces to melt metals and basically form them into particular alloys or things of that sort, you need a temperature sensor to make sure that you are at the right temperature. Basically, in this case, the only one that can be used is basically the thermocouple. Other than that, I don't think any of these will actually work. So basically, the thermocouple is used in basically metal melting furnaces, for example. Okay, so what you need to care about here for dynamic range is just make sure what your application needs, and make sure that it's included in the dynamic range of the sensor that you are planning to use. Okay. Very important concepts of accuracy and precision. Sometimes we confuse them, actually. If I told you that this instrument is precise, sometimes it comes across to you as it is accurate, right? Do you see any difference between accuracy and precision? Have you heard of any difference between accuracy and precision?
No.
Basically,
we thought it was the same thing.
They probably mean the same thing, but actually they are very different, okay? That's why we're trying to do that here. We're trying to define these things here in order for us to be able to basically compare the specifications of different sensors. Basically, if you have your reference value here, basically the reference value is the true value, okay? This is the true value. If your sensor measures this reference value, if it takes several measurements and try to basically write or draw the histogram of these measurements, for example, how many measurements were here, how many measurements were here, and so on. You draw the curve for all your measurements that you take. If the average of all measurements is here, so basically the accuracy would be the difference between the true value and the mean of all the measures that you take. Okay, so if you take 100 measurements and take the average of them, the difference between the average of the 100 measurements and the true value that you're trying to measure is the accuracy. On the other hand, let's just continue to talk about the 100 measurements that you took. The precision is basically what's related to the variance of the results. Meaning that if all of them were basically around this mean here, but actually, if they are like this, like very widely distributed like this, then this actually, the range of measurements here would be the precision, okay? So for example, when we talk about the resistance, if we talk about basically the tolerance, the 10% or whatever, this would be considered the precision of the resistance, okay? Meaning that the range around the mean of these resistors will be basically like 10% of the value, okay? So basically the precision is whenever you're taking measurements, the variance of these measurements or the wide variation of these measurements or the width of variation of these measurements are related to the accuracy. I'm going to give you right now an example, but I'm going to show you an illustration first, and then we go to the example. Let's go to the example first. I think the example would be most useful now. Basically, one of the problems that I actually gave to the student before, if I have, for example, a temperature sensor, and basically one sensor, this is like a human temperature sensor, and you took like 3 measurements, okay? One of them was like 37, one of them, or the first sensor at least was like this, one of them was like 35 and 39. The second one was basically 35, 36, 37. Okay? And basically, I'm trying to compare these two. So basically, what's the average of this? Or the mean value? 37. See, here it's up by 2 here, up by 2 here. So basically, when you add them together and divide by 3, basically going to come down to this. And here also, you notice that basically this is also the average here. 36. So each one of them, basically, if I'm measuring a temperature of 37 degrees, the true value was 37 degrees. So each one of them is more accurate.
The first one.
This is more accurate. Okay, let's talk about the range of measurements. What is the range of measurements here? The range is basically just take the largest minus the smallest. So basically the range would be what? For the first one?
35, 39.
35 minus 39, which is 4.
Oh.
Okay, how about the other one?
2.
2. Which one of them is most precise? Precision meaning that the range here is as small as possible. So basically we're talking about, basically if you put these like this here, this would be, this one here would be like this one here would be like this. Okay, so this is number 2, this is number 1. Okay, the range doesn't have anything to do with the average. The range is basically, if you look at all the measurements that you took, how wide they vary. Okay, so basically, if they have a very small range of variations, then they will be more precise. So basically, we say that the second one here is precise or has precision. Can you understand that?
Yes.
Is that clear? So the accuracy is related to the ability of the sensor to come close to the actual value, to the true value that you're trying to measure. The precision is the ability of the sensor to produce very closely related results. So basically, you have very small variations in the outcome of the sensor, regardless of whether the actual measurement that you're going to have are close to the true or not. So basically, the measurements can be accurate but not precise, can be precise but not accurate, and so on. So basically, these are two different characteristics that you have to measure for yourself, and basically, they have very important implications in your design process. Would that be clear? Is that clear? Okay. Let's give yeah, you have a question?
No, I was saying it's clear.
Okay. So let's take this example here now. Okay. This is actually like a two-dimensional example. Like assume that you have sensor, you have like you're measuring here a particular value, or here a particular value. Basically, you have your true value is right there. It's basically in the bull's eye here. Okay. In the middle. Okay. So these are the measurements here for a particular sensor. These are the measurement for another. These are the measurement for another. Okay. So here, what you're going to have here is what? In order for you to know if this sensor is accurate or not, what do you have to do? Look for the average, right? And see whether this average would be close to the actual value or not, right? So if you have measurements like this, the easiest thing for you to be able to know exactly where you will be in the average, see the range here, and see the range here, and see where you will be. Basically, if you took that range here from where there to here, you're probably going to have an average somewhere like maybe like here for all of them. somewhere like here, right? This would be, this point here would be the average of all the measurements, right? Close at least, or something here, okay? It's not going to be exactly in the middle here, right? Okay, so basically this will not be an accurate measurement, because actually the sensor average will be somewhere here that is different from here. How about the variance? We actually have very wide variations. If you look at these and compare them to these or these actually have very wide variation. You have your measurements are widely scattered around the point of average. So basically, when you have a wide range here in the X and the Y, this means that it has very low precision. Compare it to this one here, where you have very closely packed measurements. This means that you have very high precision, but unfortunately, the average of these is here, right? Average of these measurement is here. This is very different from the actual or the true value here. So basically, this will have very high precision, but very low accuracy. This one here, actually, you have the average somewhere here, and you have very tightly, very close measurements together like this. So basically, this action will have a very high accuracy and a very high precision at the same time. Okay, would that be clear for you? Is that clear for you how this is high precision but not high accuracy, and how this is high accuracy and high precision, and how this is low in both? Would that be clear?
Yes, it's clear.
Okay, so basically I want to emphasize again that precision should not be confused with accuracy. They should not be confused together. They are very different, okay? And basically, you judge them independently, completely independently. A sensor that is accurate doesn't mean that it will be precise. No, okay? If the sensor is precise, doesn't mean that it will be accurate. No, doesn't have to be like that, okay? So basically, the precision, by the way, is related to one thing that we just talked about, which is the reproducibility of the sensor, okay? So basically, this is one quantitative measure that you can use to basically get an estimate of how reproducible your sensors are, okay? So basically, if you have a high precision sensor, this means that it has very high reproducibility, okay? In this part, actually, you will usually get in the exam a particular set of measurements from two sensors, and basically you will be asked to judge them if they are accurate or precise, or which one is more accurate and which one is more precise, okay? Will you be able to do that?
Yeah.
For the accuracy, you look for the average of the measurements as related to the true value that you're trying to measure. For the precision, you don't care about the true value. You basically look at how reproducible your readings are, how close together your readings are, okay? One other thing that might also be confusing to some people is the resolution, okay? The sensor resolution actually is one of the things that might not be clear, at least for analog sensors, okay? But they are a very important issue for digital sensors, okay? When you have a digital sensor, you usually have a finite precision, you have finite word length. For example, if I'm using a sensor that will produce 12 bits of data, for example. So for example, if I have an analog to digital converter that converts volts to digital measurement, if you have a 12-bit analog to digital converter, you'll end up with a curve that looks like this. Here, basically, if you have an 8-bit sensor, you might end up with a curve that looks like this. Basically, this staircase means that all these values of the input signal will be basically mapped to 0 in the output. All these values will be mapped to 1, for example. All these values will be mapped to 2. This is the way we convert analog to digital, because analog values are basically available everywhere. Basically, between 0 and 1, you have infinite numbers. But actually, if I want to have this value or want to have this measurement inside a computer or a microcontroller or something like that, I cannot have an analog value. I have to have a digital value. So basically, this digital conversion would basically raise a problem of sensor resolution. The sensor resolution means that, you know, the more you have, the more bits you have, the more resolution you have. Okay. The resolution by definition is basically the step or the smallest change in the measurand that can produce a detectable change in the output signal. Basically, look at this here. You have to move from here all the way to here in order for you to get a change in the output to here, from 0 to 1. Okay, so you have a wide range where you have to move a lot. You have to have a large change in order for you to get from 0 to 1 in this particular sensor. Here, basically, it's very small. It's right, like much smaller than what you have here. So basically, the resolution is defined as the smallest change in the measurand. Measurand is what you measure. The quantity that you're trying to measure is the measurand that can produce a detectable change in the output signal. Okay, so if you're using a digital sensor, for example, this means that the number of bits here will determine exactly that. And basically, if you want to measure it, exactly how much it will be, basically, let's go to the notes. Basically, if you have a digital sensor, if you have, for example, let's use a smaller number of bits just to be accurate. It'll be easier for you to compute. If you have a 4-bit sensor and you have an 8-bit sensor, okay? And basically, you're trying to convert input voltages from 0 to 5 into whatever digital value here, depending on what you have here. Okay, so basically the maximum digital value should correspond to 5. Okay, so basically the resolution in the first one will be what? Be 5 over 2 to the power 4, which is what? 16, 5 over 16 here. Here it's going to be basically 5 over 2 to the power 8, which is going to be what? 5 over 256. So basically, if you look at these, actually, these two together, you'll find that this is 16 times smaller, factor of 16 here, smaller. Meaning that if you have a change of 5 over 256, which is almost maybe 0.02, something like that, just around that, okay, you will have a change by +1 in the output. Here you need to have a change of what? 5 over 16, it's gonna be almost 16 times that, 0.3, almost 0.32 actually, okay? So basically you need to have a change in the output of 0.3 in order for you to see a +1 change in this sensor. You need here 0.02 in order for you to see a +1 change in the digital output, okay? So whenever you have a digital sensor, you will need to have a higher number of bits in order for you to get a higher resolution, to have a higher resolution for your sensor, okay? If you have an analog sensor, it might not be as clear, but sometimes some sensors actually use like quantum steps. Quantum steps meaning that if you have a smaller change than the quantum step, then the sensor output might not actually produce a change. But usually for analog sensors, these quantum steps are really small, and basically they are not going to be a problem. Basically, they are not going to be that much of an issue. For digital sensors, it's much more important. So sometimes, for example, if you have a digital IC, digital temperature IC, you might find sensors that are offered with 8 bits. Sometimes you have sensors that are offered with maybe 10 or 12 actually. Sometimes it's more than that even, okay? So basically if you have a 10-bit sensor, this is more This has more resolution than this because they measure exactly the same quantity, but they actually produce an output that has a higher resolution. Okay, this will have 4 times the resolution of this. That clear?
Yes.
Okay. The reproducibility, of course, is very important. I think it's yeah, you can actually when you talk about it, you can talk about it in terms of the precision, but sometimes you talk about it in a different context when you talk about stability. Okay, meaning that sometimes if you have a particular temperature sensor, okay, that was produced like 10 years ago, sometimes there is a deterioration of the performance of the sensor over time. This might lead to some errors in the results. So basically the reproducibility or the stability means that if you take a measurement now, okay, and a measurement in 1 year and 2 years, 3 years, and so on, you will get very close together measurements, okay? The precision was talking about basically collecting a set of measurements at the same time, almost, okay? Here we're talking about a difference in time, to be talking about the stability. And you can actually divide the stability into 2 terms, either short term or long term. Short term meaning that if you're trying to get measurements over a day or something like that, okay, over 1 day, you get if you take the same exact quantity that you're trying to measure and measure it at different times during the day, you'll get reproducible results, like the results are being very close together, okay? If you talk about long term, then you're talking about taking measurements every year, for example, okay? And basically collecting over a number of years and seeing if the results are close together or not, okay? So basically this is one issue, and basically this can be actually, sometimes it's going to be, sometimes it's really very difficult to measure, but in some cases actually there are some sensors that are made to last for a long time. So basically, in this case, these are like specialty sensors, and basically, if you're going into an application that requires long-term stability, then you have to be looking for such sensors. Sometimes the reproducibility will vary depending on the measurement range. So basically, maybe if you have a particular operating range within the same dynamic range of the sensor, in one range, the reproducibility can be something, and in another range, within the dynamic range also, it can be a different reproducibility, okay? So basically, you have to actually worry about the dependence of reproducibility with the measurement range. If you're worried about that, if you have a particular sensor that you are expected to use for different measurement ranges, you have to be sure that it has reproducibility over the 2 ranges almost equally, okay? Otherwise, you'll be getting erroneous results. Sometimes people also talk about sensor linearity and offset. By definition, it's extremely difficult to get an ideal linear sensor, okay? It's usually not like that. It's very difficult. Usually nothing is linear in the universe, basically. If you look basically from a different point of view, you'll definitely find that there's nonlinearity somewhere. What we usually do, as we talked about before, we basically select a certain operating point, like the Q point in the transistor, for example. What if you remember the transistor, if you already took the first, the 311 course, electronics course, the transistor is a highly nonlinear device. But at the end, when you actually buy the transistor and work with small signals around the Q point, you will see the transistor as a linear amplifier. Basically, it amplifies the input by a factor, just a constant factor, to the output, particularly in the current. For example, you have the beta or the HFE of the transistor basically multiplies IB to give you the IC, okay, the collector current, okay? But actually, if you look at the transistor as a whole, it's definitely a nonlinear device. So basically, in many sensors, This is exactly what we do. It's a nonlinear sensor, like basically like what we saw in the thermistor, for example. It has a highly nonlinear curve, but actually when you work, if you use it, for example, for measuring temperature from a human being, then you're looking at a very narrow range around 37 degrees, from probably 35, 34, something like that, into 42, 43, something like that. It's just 10 degrees, okay, out of a wide range from minus 70 to 150, or even higher, like 250, something like that. So basically, when you're looking at a very narrow range like that, what you're going to see is something that would look almost linear, okay? And basically, the linearity basically can be measured by the deviation of the curve in the range that you want to measure from the ideal linear curve. So basically, we have to understand that it's never going to be exactly linear. So it's going to have to look like something like this. The deviation here, the maximum deviation here around the interesting point that you're trying to measure around, this is basically a measure of the linearity, okay? So when you talk about the linearity as a measure, how you measure it, basically is going to be the maximum deviation. And basically this means that if you're trying to measure over this range, the maximum deviation from linearity that you're going to get is this much value, okay? So the closer this curve gets to this curve, the higher the linearity will be, okay? If you just assume that we have the linear curve, it would look like this. Another aspect is basically whether the output will be 0 when you have an input of 0 or not, okay? This curve actually will be modeled as AX plus B. Let's go back and, okay. Basically, let's look at the curve that looks like this. Okay. This curve is by definition, y is equal to ax plus b. Okay, this is x and this is y. And if you look at this particular point when x equals to 0, you will find that this particular part of the curve basically will be equal to b. And the slope here will be equal to a, okay? So basically this part here, we will call the offset. And this offset means that when you have an input of 0, you have a 0 input, or basically we can say that this is the output at 0 input, okay? This is called the offset. This is very important because otherwise you're not going to have this curve. You're not going to know this curve. In order for you to have the relationship, the complete relationship between the output and the input of a sensor, you have to know the offset and the slope here, okay? The slope, we saw that it's the sensitivity, basically. This, we called it the sensitivity, okay? And the other part, the intercept here is the offset. You need to know both of them, okay? Usually you would like the offset to be as small as possible or as close as possible to 0, basically, okay? Because basically this means that you have an output, you have the sensor output when you have a 0 input, which doesn't make sense, actually, okay? But sometimes you cannot get rid of it, okay? And you have to accept that you have this much offset, you know, and you have to work with it in the computation of your sensor output, okay? So basically, this is one of the characteristics that you have to consider for sensors. You have to actually look at sensors and try to pick the sensor that has the smallest offset that you can get and the highest linearity, okay? Sometimes it's not that critical, but if you want to have precision, if you have high accuracy, if you want to have a really high accuracy of your measurement, you need to have the nonlinearity as close as possible to 0. Sometimes if you have an advanced measurement device, you actually don't have to assume linearity. You can actually program this whole curve. You can program this nonlinear curve and basically maybe fit this nonlinear curve with a much higher order polynomial than the linear curve in order for you to get exactly the output as related to the input. Okay, so basically the linearity is a really nice assumption if you want to have a very simple circuit to measure something. But if you want to work with something that is really non-linear and you want to have high accuracy, then program the curve and basically fit the curve. Rather than fitting the curve to a linear curve, you can consider a quadratic curve, you can consider a cubic curve, and basically get the accuracy that you want. Okay. One example of that is the measurement of oxygenation level in the blood, for example. Okay, the output from we can measure basically the concentration of oxyhemoglobin relative to deoxyhemoglobin. When you try to measure that, you get some results that have really high nonlinearity. So basically, what you have there is basically program the curve that relates a nonlinear quantity into the output that you want to have. Okay, and basically you don't have to linearize it in this case. Okay, so basically for linearity, if you want to have a very simple measurement sensor or a measurement system, you probably should target a sensor linearity. If you want to have, if you have to have accuracy and you don't care about the complexity of your system, then you really don't worry about the linearity at all. Okay, as long as you know the curve, you can actually program the curve itself inside your device and basically measure the correct value every time. Okay. The sensor response time is one important thing. Let's leave that to next time. I don't want to basically cover a lot of material. Let's go back to what we discussed at the beginning of the lecture. Probably many of you, or at least half of you, were not there. What we're going to cover in the final exam will be what we're going to cover until the end of this week. Okay, I know that you have several other courses. I know that you will be really, you know, you have so many things to do actually before the finals and in the finals, because the finals will be basically in 1 week instead of being basically distributed over a much longer period of time. So basically, what we're gonna end up having at the end of this week is basically what's gonna be covered in the exam. Starting next week, I'm gonna be available for any questions you might have. If you want me to explain any different, anything of any of the previous things, again, I can do that. And basically, I encourage you to finish all your assignments by the end of next week. Okay, so that you basically have at least 2 weeks before the end of the term, and you can schedule the final exam anywhere according to your mutual schedule. Okay, and basically let me know to actually finish the final before you get started on the other finals. Okay, so basically I would like you to discuss together a suitable time for the final. If you have any concerns about the style of the exam from the midterm, please let me know. If you have any issues with the assignment that you already have, you're going to be probably having a very small assignment for the sensors. This is going to be really easy. It's going to be things like the problem that I just showed you about the accuracy and precision, things of that sort. And basically, you're going to have the lab experiments, the simulation experiments in the lab. From what I understood from the engineer was that basically you already used a simulation program for the other experiments. If you didn't use simulation experiments for the other experiments, if you didn't use any simulations, and you find it difficult for you to find time to learn it now, I can discuss it with the lab engineer, and basically we can basically try to find something that would replace that simulation requirement in the final 2 experiments. Okay, the final 2 experiments are really simple. They are not really that hard, and I'm sure that you already had op-amp experiment somewhere else. Probably gonna have them either in 311 or 312. So I'm not worried about these 2 experiments. The most important experiments that are related to the course, you know, were included in the experiments 1 through 5. So basically, from now until next time, please discuss with the lab engineer what you should be doing in experiments 6 and 7. And if you find it difficult, let me know next time. Okay? The final, please basically discuss together a suitable time for the final. once we finish the material for this particular lecture, the lecture we're having, and basically by the end of this week, I'm going to send you a list of topics, very specific topics that will be included in the final. Okay, so basically it's not going to be everything that you had from the start of the term until now. No, it's going to be like a selected set that I think would be the most important for you to have at the end of this course. So basically, I'm going to basically include the topics and the subtopics that are important for you to look at. Okay, so that when you prepare for the final, you will be actually directed to the, basically you'll be guided to basically what should count in the final. Okay, you have any questions or concerns?
No, thanks.
Okay, so inshallah next time on Tuesday I expect you to please let me know your feedback about the simulation experiments. Maybe try hopefully by next week or at the end of the week, by at most. Let me know exactly what your plans are for the final exam, and please, if you didn't submit your lab experiments, please do that. I probably think that there are at least 2 groups that haven't done that yet. Okay, I counted the number of students from the that were included on the lab experiments that I received. I actually think that there might be some, at least maybe 6 or 7 students that haven't submitted their group reports yet. Please do that so that we can give the engineer enough time to grade them again. Okay. If you have any questions in your submission, let me know. If you have any difficulty submitting your reports or anything like that, please let me know. Okay. And please be careful because actually we're going to have the curfew starting at 3. Okay. So if you are outside, you should go home at as soon as possible because of the Manat Tijwal. Okay. It's going to start at 3 today, not rather than 6. Okay, rather than 7. Okay, so basically, I heard about it by chance, but actually, I'm sure that some people actually haven't heard about it. So basically, try to go home as soon as possible. Okay, and stay safe, please. Okay.
Okay.
Thank you, Dr.
Okay. Good luck, inshallah. Good luck, inshallah. Shukran. Assalamu alaikum.
Thank you, Dr.